Hello, everyone. So, yeah, today I'm going to talk about the first formal lecture on multi-agent systems. I'm going to look at a simplified version of consensus and synchronization problems, what they are, um, how do we classify. First, before even I start, I would like to look at the simplest dynamical system, scalar integrator system. X is the state, U is the control variable, some initial condition. And here, let's say the control structure has some form of like this, minus x, minus plus comment. Minus x is the feedback component, plus c is some constant comment that we inject. And minus feedback stabilizes the system. And because of this presence of comment, there will be some input to the system. So if you write the closed-loop system, it will look like this. You can group it under the minus sign in parentheses. What this means, if you are familiar with those dynamical systems here, X will try to drive its value to comment. So state eventually will approach to this comment. And you can even, analyze its equilibrium point. If you set when the motion stops, x that equals to 0, x becomes c. So, and since you have negative feedback, stabilizing feedback, you expect x to go to its equilibrium point, in this case, the comment c. If you're not familiar with equilibrium points, you don't have to, you can directly solve this expression, and the solution to the system, it is looking like this. After some transients, depends on the initial condition, will disappear. This term will also disappear. As t goes to infinity, x will approach to this comment. And if you don't want to look at the solution, that's fine. You can look at the Lyapunov analysis. So construct an error. Since we engineeringly inspect x to converge to, we intuitively realize x will approach to this comment. So I construct an error signal, taking its derivative to form the error dynamics. E dot becomes x dot minus c dot 0, because we assumed it is constant for now. And so E dot becomes x dot is minus x minus c, which is the definition of the error. So E dot is minus e. You can consider this positive definite Lyapunov function candidate. It is positive definite for all x except e equals to 0. When e equals to 0, v is 0. It touches the 0 point, and it is radially unbounded. So it is the proper Lyapunov function. And once you take its derivative, v dot becomes e dot. There is 2, cancel out with this 1 over 2. So e dot is minus e. Once you insert it, we have minus e to the power of 2 less than 0. So you have a positive energy, you dissipate your energy. So system is asymptotically stable. Actually, in this case, you can also claim exponential stability, but that's not important for the sake of this discussion. So I showed you here error goes to 0 asymptotically. So again, you can intuitively inspect from here, or you can learn convergence to the comment by looking at the ecliptic solution or some Lyapunov error dynamics based analysis. So basically, this is a single system. It starts from some initial condition. After some time, it approaches the comment. This was one system. Again, X approaches to C. Now, I will consider two agents, but we don't have external comments like C. Instead of having X minus C type of a structure, here we have two control laws. The first agent, state of a first agent, tries to drive itself to the second agent, think like as the comment to this system, but right now it is no longer a constant command, it's the state of the second agent. Likewise, second agent, it has a feedback component like the first agent, but tries to drive itself to second agent. So here, if you write the closed-loop system, x1 dot is depends on x2 in addition itself, likewise x2, we inspect just by intuitively the state of both agents will try to drive themselves to each other. So engineeringly, if you want to use a Lyapunov type of analysis, since you intuitively inspect x1 and x2 to approach to each other, you can form an error signal. And you can look at the E dot. E dot in this case, x1 dot minus x2 dot. X1 dot is minus x1 minus e2, so minus e coming from the x1 dot, minus x2 dot, so minus, this is the x2 dot, minus x2 minus x1, which is the, you can write it at x1 minus x2, so this is like e. And if you have e with minus sign, you have another minus e minus e minus e minus 2e. So v dot dot v dot becomes e dot, and e dot is minus 2e. Once you inject, you have minus 2. There's a typo here. This should be 2. Minus 2e to the power of 2. Again, less than, strictly less than 0. So you have asymptotic slash exponential stability. Error goes to 0, meaning that x1 and x2 approaches to each other. Well, all right. So now to quantify this, we can do a plot like this. I will also explain this here. But let's say you are starting from x1, x2, these two initial conditions. You basically approach to this 1, 1 line, and here x1 equals to x2 at some value. But the final convergence point in this case will depend on your initial conditions. So if you start from this x1, x2 initial set, you will converge to this point because it has to write x1 must be equal to x2. And 1 x1 equals to x2, you have this line at 1, 1 expression in this line x1 equals to x2. Now, if you start from another initial condition, let's say here, x2 is negative, x1 is positive, you will still converge. You have to. x1 must be equal to x2 eventually based on this Lyapunov analysis. So your final convergence type in this example depends on your initial condition. You still do the job, x1 will converge to x2, solving so-called the consensus problem. Also go with the names like the rendezvous problem or agreement problem. It is a very fundamental problem. We'll illustrate for 2 agents later. We're going to do for more agents. But the point is, in this consensus type of a problem, if there are no external comments to the agents, if agents control actions only depend on each other's states, then they all converge to a common value. And that common value, you know, at that common value, x1 will be equal to x2. Later, when you have more agents, all the states will be equal to each other. But the final value of that state, when x1 equals to x2, depends on your initial conditions. And this notion is explained so-called semi-stability. So to understand semi-stability or dependence on your final convergence point based on your initial conditions, we can write this system, closed-loop system, into this state space form x1 dot equals to itself minus x2. Likewise, the x2 dynamics here, you can write it in matrix vector form like this. And this A becomes our system matrix. And since A is the system matrix, we look at the eigenvalues for convergence. In this case, you have a 0 eigenvalue and A has another eigenvalue, which is at -2. Now, semi-stability is a notion that goes like this. If you have a system matrix with 1, 0 eigenvalue, and let's say all the other eigenvalues have negative real parts, they can be complex as well, then solution will escape to the null space of your system matrix. And in this case, that null space corresponds to the agent having the eigenvalue being the 0 eigenvalue. So this basically null space also is the eigenvector corresponding to the 0 eigenvalue. So a solution will escape to this null space of the system matrix or the eigenvector of the 0 eigenvalue when you have 1 0 eigenvalue or a simple 0 eigenvalue as t goes to infinity. So how we can find the null space? You can find the null space by basically invoking. If you have a matrix, you are seeking for a non-zero vector such that once you take this matrix multiplied by v, you get 0. So in this case, since this is the A matrix, if you multiply it by v1 and v2, you can guess, for example, if v1, v2, 1, 1, you are going to get 0, 0. -5, -5, you get 0, 0. 10, 10, you will get 0, 0. So there exists more than one unique V1 and V2 pair. That's why we use this span. So V1 and V2, or the null space of this A matrix, or the eigenvector of the zero eigenvalue, spans all vectors that are 1, 1. Here, span means it can be 1, 1, 2, 2, -5, -5, anything that, you know, if you consider, for example, -10, -10, yes, you can write it -10, -10 as -10 multiplied by 1, 1. So -10, -10 vector spans this 1, 1 vector. Anyway, this 1, 1 vector is where x1 equals to x2. This represents this line. Once again, this line comes from the Liponov analysis. This line also comes from this null space of A, or the eigenvector of the zero eigenvalue. Again, this is the consensus problem. There are no external inputs to the systems. Each agent tries to drive themselves to their states without any external commands, so they converge to a common value. X1 becomes X2 eventually, here or here or here or there. Final point can be anything depending on your initial conditions. And since you are not converging to an equilibrium point, like in this example, right, X converges to C, it is fixed. It doesn't depend on your initial conditions. Regardless of where you start, it will converge to C. It is not semi-stable, it is asymptotically stable. In this case, it is semi-stable. Your final point depends on where you start. Your error dynamics in this case, asymptotically stable, but this system, if you analyze X1 and X2, this system is semi-stable. So again, I don't want to confuse you, but error goes to zero. Error is asymptotically stable. Goes to zero. It goes to zero. So error dynamics is asymptotically stable. But this system is semi-stable, because if you characterize convergence point not based on this error, but based on your states, your final value of x1 and x2 can be equal to 1, can be equal to -2, depending on where you start. So equilibrium is semi-stable in this sense. If anything doesn't make sense, you can always leave a comment and ask questions so that I can further answer your questions or comments in the uh, uh, eh, in my replies. So now, okay, we look at the first problem, which was a simplified consensus problem. We didn't have any leaders. Now I need to define what do we mean by leaders. Sometimes in a multi-agent system like this, I consider the same setup here, same control actions, but now I am injecting the external command back to the system. External command only available to the first agent, not to the second agent. Now, if you look at here, x1 tried to derive itself to x2, x2 tried to derive itself to x1. Yes, like the previous consensus case. But now we have the external comments. When you have external comments, agents that these external comments are available are called the leader agents. In this case, the first agent is the leader. The others are followers. Now here, in addition, x1 tries to drive itself to x2, it will also drive itself to command C. So what's going on? X1 will try to itself to both x2 and command, and x2 only tries to drive itself to x1. So eventually, engineeringly, if we think about with some intuition, what should happen is that x1 will approach the x2 and the command, and x2 will approach the x1. But since x1 also approaches the command, x2 will approach to both x1 and command. Here, since x1 is the leader, its convergence to command can be more direct since it uses it as another feedback control signal. X2 indirectly, by following x1, this follower should follow that leader. So again, here in this leader-follower setting, I would like to distinguish one more time, because we're going to discuss in what follows more in detail this consensus uh, or leaderless networks with leader follower or synchronization networks. This is the synchronization problem. Because in the synchronization problem, your final convergence point depends on your input or external commands available to the leader agents. Your final convergence point will not change based on your initial conditions. If x1 and x2 can start from any other arbitrary initial condition, once you execute this protocol, leader and follower protocol, it has the consensus type of dynamics, but now each agent will try to synchronize themselves with the comment available to those leaders. That's why it is called leader follower or the synchronization problem. Again, the main motivation of these introductory slides, I'm going to try to introduce you to the consensus, synchronization. In consensus, we have a leaderless network. When what we mean by leaderless, there are no external comments like C. What I mean by leader follower, we have the consensus like dynamics, yes, but we also have some agents taking inputs, knowing to trying to synchronize themselves with these commands. So it is the leader agent. So since we have a now synchronization problem, it is not useful to look at the error x1 and x2 because yes, x1 and x2 goes to each other, yes, but not like arbitrarily, unlike the consensus problem. If you like, you can differentiate this e dot. You are going to have, after some mathematical steps, I'm not going to explain, you can pause the video and look at. So E dot, if error is like this, you have minus 2E like before, but you have another term. This acts like a perturbation, which makes it is hard to analyze with this type of error dynamics when you look at synchronization or leader follower problems. So for those problems, I'm going to use, in this case, I'm going to define two error variables. E1 is x1. I know x1 approaches the command, and I know even indirectly x2 approaches to this command. So for follower and for the leader, I'm going to define same error based on their distance between their states and the command variables. If you differentiate E1 dot, x1 dot becomes C dot is 0, x1 dot was here, this guy, or this guy here. I am adding and subtracting C here because this becomes E1, this becomes minus E2, and this is already minus E1. Simple trick that helps me to write everything in terms of errors. Because, with this state transformation, I would like to get rid of all x1 and C. I don't want terms like this. I want everything to depend on either E1 and E2 so that I can analyze. I am doing the same thing for the E2 dot, taking the derivative, forming the error dynamics for the second agent, x2 dot minus 0. x2 dot is here, minus x1, x2 minus x1. I am adding and subtracting comment here because this makes E2, this makes minus E1 after the minus sign, minus E2 plus E1. I consider this Lyapunov function candidate. It is proper. Right now, it has two entries because now I have two error dynamics, E1 dot and E2 dot. I no longer have one like the previous case. And it is radially unbounded. It is 0 when E1 and E2 is 0, otherwise positive definite. So it is proper. I'm taking the derivative, E1, E1 dot, E2, E2 dot. I am injecting E1 dot and E2 dot equations from above, and I have this. So in this Lyapunov derivative, I have two negative quadratic terms, beautiful, but I have one sign indefinite term. When you have sign indefinite term, one of the practical approaches is to apply Young's inequality. If you are not familiar with such tricks, you can go to, on my YouTube channel, go to the Advanced Control Systems lecture series and watch the video called Stability, Lyapunov Stability and more. I cover all the details, including Young's inequality and more. If you have any questions, you can leave a comment. Anyhow, I apply Young's inequality to this sign indefinite term, which makes it sign definite for any positive mu. Young's inequality holds for any positive mu often called as Young's constant. So once you insert this, once you upper bound this term like this, you are going to have these expressions. Now here, mu is arbitrary. I need to choose it in such a way that I am preserving this and this minus sign. So if you select mu to be 1.5, this becomes 0.5, this becomes 0.34. So this is nice negative terms containing both of them. You can claim asymptotic stability / you can also claim exponential. In this case, after a couple of tricks, but asymptotic stability is good enough for us for now. So which shows that E1 and E2 goes to 0 as t goes to infinity, meaning x1 follows to command, x2 follows to command. And if you pictorially draw this, you have this figure. I went more than I should. We're gonna discuss graph theory fundamentals. This one that I showed you next lecture. And in the next lectures, first, I can say upfront, first we're gonna look at graph theory. And for this, in this slide, I would like to talk a little bit about graph representations of these two agent systems. But we're gonna dive into more graph theory fundamentals in the next lecture. For now, graphs basically model how agents exchange information with each other. For example, consider this graph. This represents the consensus dynamics when we have no leader, no external commands. So this is a leaderless configuration. Agents, protocols, control signals depend on each other, no external commands. And here X1 receives information from X2, which is X1 receives information from X2, or there is an information coming to X1, X through X2. This arrow bottom shows that. Likewise, the up arrow, X2 is affected by X1. So this arrow shows that X2 receives information from X1. So this representation X1 minus X2, X2 minus X1 are directly related with these arrows. And in this case, since both agent 1 sends information to agent 2 sends to agent 1, this is an omnidirectional or bidirectional information exchange. And since both, there are both arrows, this is called undirected graph. Information flows in both ways. So instead of writing it, representing with two arrows, you can just put an arrow without any arrow signs, just in this case, solid line. What I mean, if you have a solid line, it means this. So instead of writing like this, in the literature, we usually put a solid line if the information flows in both directions. And in the upcoming lectures, we're going to use this. This was the consensus case with simple two agents. And the leader for lower case with simple two agents also looks like this. And right now, this is the synchronization problem since you have a leader, the first agent knowing the command. And here, same graph captures the information exchange in here. Now, you also have a directional arrow, meaning that X1 is getting affected by C, but still the information exchange between agents are subject to undirected graph. We call it graphs as the undirected versus directed, depending on information exchange within each other, not like externally. So I don't want to call it directed graph. We shouldn't call it directed graph because this is not coming from an agent. Forget about this. This is bidirectional. If this is bidirectional, we can represent with a solid line, meaning agent flow information flows in both ways. So we call it an undirected graph. I'm going to talk about directed graph in the graph theory fundamentals video, the next video. And after that, we're going to look at more in detail this consensus-like dynamics first, and then synchronization-like dynamics second. And again, consensus applies when you have no leaders, no external commands, they know of the agents, and leader follower when some agents know the command and tries to also synchronize themselves with the command. So this is the leader in this case, and this is the follower. Anyway, we're gonna look at more in detail synchronization problem. All I want you to learn from this video, if you remember one thing, consensus like leaderless problems, in all cases, agents converge to a common value, but that common value is based on their initial starting points. If you start here, you converge there. If you start here, you converge there. If you start here, you converge here. They converge to each other. X1 equals to eventually X2. Yes, but convergence depends on the initial point. Versus synchronization point, every agent synchronize themselves within a command, and that command in initial conditions can be anything. X2 can be anything, X1 can be anything. When you run this protocol, regardless of the initial conditions, all agents converge. The trajectories, the states of all agents converge to a generated command or a command known by leader agents. That's the fundamental difference between consensus and synchronization-like problems. And again, we're going to look at graph theory fundamentals and then consensus dynamics for more than two agents, and then synchronization dynamics for agents more than two agents. In fact, what we are going to look generalizes to any number of n number of agents more than two. So let's catch up in the next videos, and leave a comment if you have any questions. Thanks.